Hello and welcome. In this section, we'll discover how assembly language fits into modern software development, specifically within the Windows environment. We'll guide you through creating Windows console applications, see how to use the Irvine 32 library alongside the Windows AP. I learned how to set up and debug your projects in Visual Studio, and finally, we'll cover some of the common errors you might encounter in assembly programming. Let's begin with creating Win32 console programs. So far, we've mostly used the Irvine 32 library, which simplifies many tasks. However, MASM can also create full Win32 console applications that interact directly with the Windows Application Programming Interface, or a PI. The key difference is that we will explicitly call Windows API functions like write console and read console instead of the Irvine 32 helper functions. Our programs will also have a main or WinMain style entry point and will be linked against Windows system libraries like kernel32.lib and user32.lib. Let's look at the structure of a minimal MASM Win32 console program. The code starts with the usual directives, .386.modelFlat, stdcall, and option casemap : none. Then we include windows.inc and kernel32.inc, and we also specify that we need to link with kernel32.lib. In the data section, we define a message string. The main procedure begins by getting a handle to the standard output console. We do this by pushing -11, which is the constant for standard output handle, onto the stack and calling the getStdHandle API function. The handle is returned in the EAX register, which we then store. Next, we call the write console A function to print our message. This function requires several arguments to be pushed onto the stack in reverse order: the console handle, the address of our message buffer, the number of characters to write, a pointer to a variable that will receive the number of characters written, and 2 null values for reserved parameters. Finally, we call the exit process function with an exit code of 0 to terminate the program cleanly. To use Windows API calls in MASM, you typically need to include windows.inc, kernel32.inc, and user32.inc, along with their corresponding library files. These files contain the necessary definitions and function prototypes. For console applications, some common API functions are getStd, handle, write console, read console, set console cursor position, and set console text attribute for changing text color. To build a program like this from the command line, you would first assemble it using ml.c.conf program.asm and then link it using link subsystem : console program.obj. Learning to do this gives you direct control over the Windows API and is a great foundation for moving on to graphical user interface or GUI programming. While using the pure Win32 API is powerful, it can be tedious for simple tasks. The Irvine 32 library was designed to make assembly programming easier, and you can actually use it within Win32 console applications. This hybrid approach allows you to use convenient functions like write string and read int for quick prototyping, while still having access to the full Windows API. For more advanced features that Irvine 32 doesn't cover, like setting custom text colors, let's look at an example that mixes both. The code includes both Irvine32.inc and kernel32.inc. We can use write string from the Irvine 32 library to display a message, and then directly call the set console text attribute API function to change the text color. To do this, we first get the console handle using getStdHandle. Then push the desired color attribute and the handle onto the stack before calling the function. When you use this approach, you should always include irvine32.inc first, and remember to link your program with irvine32.lib. This method is great for learning and for building small console utilities where you want a mix of convenience and power. Now, let's talk about running your programs in Visual Studio. While the command line works, Visual Studio provides an integrated environment with a code editor, syntax highlighting, one-click building and running, and most importantly, a powerful debugger. To set up a project, you'll need to have Visual Studio installed with the desktop development with C++ workload. You can then create a new empty C++ project, add your .asm file, and configure the project's build customizations to use the MASM assembler. If you're using the Irvine 32 library, you'll also need to configure the project's properties to tell the linker where to find irvine32.lib and the assembler where to find irvine32.inc. Once set up, you can build with Ctrl+Shift+B and run with Ctrl+5. Debugging is a critical skill in assembly programming, and Visual Studio's debugger is an excellent tool for it. Debugging assembly is like detective work. You have to track values and registers in memory at every single step. A single wrong instruction can crash your program. To prepare your program for debugging, you need to assemble it with debugging information. The MASM command line switch for this is /ZI. Once in the debugger, you can set breakpoints to pause execution at specific lines, and then step through your code instruction by instruction using F10 and F11. As you step, you can watch the values in the registers window, inspect memory locations, and check the call stack. Common techniques include checking register values after each instruction, monitoring the flags register to understand the outcome of comparisons, and even inserting temporary output calls to print values at runtime. Finally, let's cover some of the common errors in assembly programming. These errors generally fall into three categories: syntax errors, runtime errors, and logical errors. Syntax errors are caught by the assembler when your code doesn't follow the language's rules, like misspelling an instruction or using the wrong operand type. Runtime errors happen while the program is running and usually cause a crash. Examples include dividing by 0 or trying to access a restricted memory address. Logical errors are the trickiest to find. The program runs without crashing, but it produces the wrong result. This could be due to using the wrong jump condition, forgetting to initialize a register, or having an off by 1 error in a list. The key to fixing these is careful debugging. To avoid errors, it's good practice to comment your code generously, always initialize your registers, balance your stack pushes and pops, and test your code in small incremental steps. This concludes our section on integrating assembly into Windows programming. Thank you.